All right, let's talk about inference. We're going to begin this by looking at an example and talk about foundational ideas about inference, inference about a population. So essentially what we have is you have a population of interest and we gather some sample data from that population in whatever means we have, probably a survey, and then we're going to take the information we learn from the survey and try to make some sort of conclusion about the population. That's inference in a nutshell. So let's take this example of the Youth Risk Factor Behavior Surveillance System, YRBSS. So it's a survey conducted by the US CDC to measure health-related activity in high school-aged youth. So so 2.6 million high school students participated in the years 1991 to 2013. In 2013, we have the data. We have 13,583 responses in this YRBSS data set with 13 variables. So each row is like a single participant's responses to the 13 survey questions or things about that person. So an example, you'd see age, gender, grade, height, weight, and some other things. So here is it's just showing a few of the variables. Columns 1 through 3, 6 through 8, and 10. Okay, so this will give you just a sense of the kind of data. And this is what we're going to be looking at: the age in years, gender, male or female, grade in high school, height, weight in meters and kilograms, the frequency that the student wore a helmet biking in the last 12 months, and the number of days physically active for 60 plus minutes in the last 7 days. So these are the other variables, but let's focus just on these. So for each of these, we're interested, there's going to be some parameter within the population that the sample data is going to hint at, right? So what some characteristic of a population is what we call a parameter. For example, the mean weight. The mean weight in the population is a population parameter. We're going to use Greek letters for the population parameters, and for sample statistics, we'll use English letters. And for the sample mean, we'll use this X with a bar over it, X bar. So in this case, we don't know the mean weight for the population, but we have the sample mean weight, and so sometimes you use a subscript for denoting which variable you're talking about. So this is just some notation. If you're trying to make an estimate of the population parameter, there's a couple kinds of estimates we'll look at. The simplest is called a point estimate, and that's where we just try to get a number that's as close as possible. And the best point estimate turns out to be the sample mean. So the sample average is the best point estimate of the population average. And that can be proved using mathematical statistics theory stuff, but it turns out it is actually the best point estimate. So like I said, this trying to estimate the population mean, which is a population parameter, from the sample mean, that's an example of statistical inference. And so the one concept that's really important to think about with respect to statistical inference, because we're estimating the population parameter from our sample mean, our sample mean is really a sample mean calculated from a relatively small portion of the population. So 13,000 individuals, but it's the population's 2.1 million, right? Suppose in an alternate reality, we were to have sampled a different 13,572 people, right? Every sample of 13,572 people would have resulted in a slightly different sample mean, maybe quite largely different sample mean, but a different sample mean. Every sample we could have drawn would have given us a different sample mean. But if you look at all of those sample means that we could have gotten, and we were to kind of look at the distribution of those sample means, what we're looking at, like picture a histogram now in your mind, that distribution is what you call the sampling distribution of the sample mean. So knowing something about its sampling distribution can tell us something about how far our point estimate might be from the population parameter. So to kind of demonstrate this, we'll be doing this in lab, but because the population parameters are unknown, we can kind of simulate sampling from a population by taking, so let's take this 13,000 individuals and consider them our population. And let's look at some very small samples from this population. We're going to be able to simulate taking small samples of size like 10, for example, from this. And what we can do is look at how far away the average from these little samples is from the average weight of the whole population, and we can look at we can construct a sampling distribution. Now, there's actually theory about the sampling distribution, but we'll kind of develop some intuition about that from simulation first. Here's an example of the code that you would use in order to do this. Now, here, the idea is that we're going to take the data frame as the population. We'll just use the sample function to sample from the entire. What we're doing is when we said sample.rows, that's what rows we're going to be sampling from. That's going to create a little vector of the sample size. It turns out 10 in this case. 1:n row YRBSS, that is, take all the numbers from 1 up until the number of rows, which is like 13,000 something. So it's going to sample 10 numbers from this list of numbers possible, and then you get the rows. So when we do mean of the of YRBSS $weight, that's the average weight for only those sampled rows. And we can get the mean and the standard deviation. This is, now we can now compare we can think about how we can see how that mean and the standard deviation compare to the population based on the sample size and stuff like that. That's going to be part of the lab. So if we're going to be plotting plotting a histogram to get us approximate sampling distribution for a sample size of 10. What's important to remember is the sampling distribution for the sample mean depends on the sample size. So a sampling distribution would be specific to a sample size of 10 for this case. And then we're going to kind of look at the theory about what is the theoretical, properties of the sampling distribution. So the idea is we can treat our sample mean as a random variable. And as a random variable, it has a mean and a standard deviation, and actually it has a probability distribution. At least theoretically it does. We'll see that in practice the distribution matches the theoretical probability distribution pretty closely, and we'll observe in class that as the sample size gets bigger, the variability of the sample mean gets smaller and smaller, which is to say that with a larger and larger sample size, you're less likely for the sample mean to be very far off from the population mean. We'll talk a little bit more about the specifics of that. Okay, so then with some knowledge about the sampling distribution of, say, the sample mean, we can do better than just giving a point estimate for the population mean. We can actually say, rather than guessing a certain number, we can say, I'm pretty sure that the population parameter is between this bound and that bound. So giving an interval that we're pretty confident contains the population parameter. This is called a confidence interval, and it can be calculated using some formulas or using some functions in R, and we'll talk through those. But the idea is that you take your sample mean, and then you add and subtract some margin of error. And the margin of error is calculated based on what is the standard deviation within the sample, and it has to do with the sample size and how sure you need to be that your interval correctly estimates the population mean. So we're going to go through some of the notation to be really clear. So again, the mu, the Greek letter mu, is the population mean, and that's going to be unknown for us. Also unknown would be the population standard deviation. We use the Greek letter sigma. Okay, we've looked at these a little bit before. So n would be the sample size that we're drawing from the population. X bar, that's the sample mean, and lowercase s is the sample standard deviation. So we draw a sample of size n, we could calculate the sample mean, the sample standard deviation. Now there's this probability distribution called the t distribution, which is fundamental to this statistical inference on the population mean at least. The t distribution is a distribution that is bell-shaped, but it's a little bit different than the normal distribution. It's centered at 0, and it has a standard deviation of 1, but its tails are a little fatter than the normal distribution. And how fat the tails are depends on the degrees of freedom, which is the one parameter in this distribution. As the degrees of freedom increases, and around 25, 30, it's really hard to tell the difference between the t distribution and the standard normal distribution. But for lower degrees of freedom, the t distribution is noticeably fatter tails. Now, the degrees of freedom is going to be calculated based on the sample size. In fact, for what we'll be doing for making an inference on the population mean, the degrees of freedom will be 1 less than the sample size, so n minus 1. Here's an example of a t distribution. It's quite lovely looking. What we have here, you can see how so in the dark blue is the normal distribution, or the Gaussian. And if you start at the lowest peaked distribution, you have a t distribution with only 1 degree of freedom, which has very fat tails. And as the degrees of freedom goes up to 2, to 4, to 8, you can see the peak rising and the tails thinning out. And this is what we mean when we say the t distribution. It approaches the normal distribution. And as I mentioned before, a lot of probability distributions actually, their limiting distribution, or they converge to the normal distribution as some parameter increases. Okay, so this is going over a formula for a confidence interval. Now, typically we will kind of set some level of confidence that we're interested in, say 95%, which is to say I want to come up with an interval that I am 95% sure contains the population mean. And that can be found by setting the margin of error to be this t star times the standard deviation over square root of n. T star is it's finding the critical, like this value in the t distribution where we're collecting 95% probability in the middle, or like the middle 95% is found. And that can also be found by taking the 0.975 area to the left. So we'll have code for that, and we'll go over it in class. Now this s over the square root of n, that's called the standard error of the mean, and that's the sample standard deviation divided by the square root of sample size. So this actually shows you that if n gets bigger and bigger and bigger, then your margin of error is going to get smaller and smaller and smaller. So anyway, this margin, that's how the margin of error is calculated. You'll get the sample mean plus or minus that margin of error will give you the lower bound and the upper bound. We typically give a confidence interval using this notation where you have a parenthesis, the lower bound, comma, upper bound, parenthesis. That's common notation that's used. And so again, what we mean would be that we're 95% sure that the population mean is between this and that. Here's the code for finding that critical t-value. This is found using the t distribution. That we want to find the quantile going corresponding with 0.975 probability to the left. So it'd be qt. That's the quantile from the t distribution, 0.975, and then you have to set the degrees of freedom. df equals 9. So in this case, if we found the standard deviation to be 10.031 and you found the sample mean to be 63.639, the 95% confidence interval gets calculated to be from 56.46 to 70.82. So we're saying that we're 95% confident that the average weight of the high school students in the population is somewhere between 56.46 and 70.82. And this is, whereas if we were just giving a point estimate of 63.69 or 639, we couldn't say, I'm 95% sure this point estimate is correct, right? A point estimate is by its very nature incorrect. We can be pretty darn sure that the point estimate does not hit the mark exactly. But if we give an interval, we can say with 95% confidence that the interval captures the parameter we're interested in. So this is you can use the t.test function in order to calculate a confidence interval really quickly, and we'll be going through that. So you don't actually in practice have to use the formula. You can use a function called the t.test to calculate the confidence intervals. So what you'll see some places is a confidence interval given as a 1 minus alpha times 100%. CI means confidence interval. So the 1 minus alpha is like, if I was saying 95%, the alpha would be 0.05. So how far are we from 100? That's 0.05, or from 1, I should say. 0.05 would be the corresponding alpha. And so to find the critical t-value, you would use 1 minus alpha over 2. That's how you would get, how we got that 0.975. 1 minus alpha over 2. Okay, now this is actually coming from what's called the central limit theorem, which says that the standard deviation of the sample mean as a random variable is the population standard deviation divided by the square root of n. This is what you call the standard error of the sample mean. Now, we just are estimating the population standard deviation using the sample standard deviation, and that's a pretty close estimate usually. And it turns out that if we actually knew the population standard deviation, which we actually never know, we have kind of tighter results where we would know that we would know something about the distribution, but forget I ever said that, because we never know the population standard deviation for sure. We just would have the sample standard deviation. So this is called the standard error of the mean. And this is coming from the central limit theorem. We'll talk about it more explicitly later. So the confidence interval, the confidence level, sometimes called the confidence coefficient, this 95%. The idea is to say that if we were to run the confidence interval with 100 different samples of the same size, we would expect 95% of them to get the parameter within the bounds of the interval, right? That's the idea. Of course, we're not really sure whether or not we're right. All we can say is we interpret this as being 95% confident, right? Let's see. A couple little things when we're doing this inference, it's assumed that the samples are true random samples, and that the population isn't like changing. I know this says the target population is well defined. So, well, the population means not known. The target population has to be well defined. So, like, we are only sampling from one population, and also that the samples that we're drawing are representative samples from the population, not like biased samples or something like that. So, and of course, it's like independent random sampling. So we're not only selecting from one small cluster of the population, for example, or so if we're doing like a convenient sampling, that's probably not going to be independent sampling. So in practice, it might be hard to get these to be truly done, but we do our best in practice. So the second type of inference, well, the first type of inference was an estimation, estimating population parameters, confidence intervals. Now we're going to look at the second kind of class of inference, which is decision making, deciding whether this is or isn't true about the population. And we call that hypothesis testing. So you could ask a question like, on average, are Americans overweight? Okay. And so we could ask this question based on body mass, the body mass index. Remember, this body mass index is the weight over the height squared. So if it's in kilograms over meters, and if you have it in pounds and inches, you can just multiply it by 703, and that will be the conversion to kilograms over meters squared. That's what this is saying. So the classification for overweight would be a body mass index over 25, okay, greater than or equal to 25. And so if we're saying on average Americans are overweight, that's like saying the average weight of Americans is greater than or equal to 25. Okay. So we're going to use some different survey data. The National Health and Nutrition Examination Survey, NHANES, and Haynes is another survey done. And we have 10,000 participants, data from 10,000 participants in this data package we'll be using. And so random sample 21 and older individuals. We can to explore the ideas of inference, we can consider this data set of 10,000 to be actually a small population of 10,000 individuals, and we can make smaller samples from that data set. Here's an example looking at the body mass index for individuals, and it looks like for these are for Americans. We have the median is 27.9, the maximum is 69. Looking at that, the mean of 29.1 is above 25, but the question isn't whether the sample mean. This would be like the population mean. So this is, if we're treating this data set as our like mini population of this kind of shrinking the United States down to 10,000 individuals, this is going to be our our population mean, 29.10. This is just so you have a sense of what the body mass index distribution looks like in this population, right? So it definitely is a skewed distribution. You can see it tails off towards the higher end with some individuals who are have a particularly high body mass index. So we could so we're going to look at the idea of hypothesis testing. You could sort of use the tools of confidence intervals to try to do a hypothesis test. I'm not very keen on that, so I think I'm going to skip over that and then we'll just spend our time on the formal logic of hypothesis testing. So the idea would be that we have really that we take the approach that there's really two possibilities. Either we have the data is being drawn from a null distribution, or it's drawn from an alternative distribution. So the null distribution, a distribution that maybe has been true in the past, for example, or where the mean of the population is is known to be it's assumed to be some value that was the mean in the past. And the alternative distribution is some other distribution introduced by an intervention or a changing condition, or some sort of hunch or something like that. So we're trying to see whether the value of some statistic from the population is so extreme it would be unlikely to occur under the null distribution. This is the idea. We sort of assume the null hypothesis or the null distribution to be the case, unless the data is so strongly refutes that we would be forced to reject it. So the idea is we are assuming the null to be true unless it can be convincingly proved otherwise. So this is the idea formally. When you're doing a hypothesis test, you kind of formulate your null and your alternative hypotheses. So describe the parameters of your null and alternative populations or distributions. Set a significance level, this alpha, and it's going to be the same alpha that we talked about earlier. Talk a little bit about more alpha later. You get a test statistic, and the test statistic is going to be some statistic that's coming from the data that has a known sampling distribution, and that's going to be useful for determining how extreme it is. So like if your test statistic comes from the tails of the distribution, then that's considered to be a very unusual observation under the null hypothesis. So we assume the null hypothesis so that we get what would be the distribution of test statistics under the null hypothesis. Where does our test statistic lie? The p-value is a measure of how unlikely the test statistic would be in the null distribution. And then we make a conclusion. We decide whether or not the data is strong enough, or the evidence is strong enough for us to reject the null. That's the idea. So the null hypothesis, we use the notation H with a subscript 0. We call it H naught. It represents the status quo, or no change from the past. It's the least interesting of the two possibilities. Whereas the alternative hypothesis, the notations vary from book to book. HA, H1 sometimes, could be lowercase or capital A, but it's a real different distributions, and so the alternative hypothesis is modeling kind of the hunch that we're interested in proving. So the alternative claim would be put in the notation of the alternative hypothesis. So, for example, we could look at the null hypothesis that the mean BMI is 21.7. That's the midpoint of the normal range. And then the alternative is that the mean of the BMI is greater than 21.7. So the value that we're putting in for the null hypothesis is we could call that mu naught. And we're always going to have the null hypothesis have the parameter equal to some value, equal to some null value. Because we need to specifically be able to calculate the distribution under the null hypothesis. So we need to know what is the parameter under the null hypothesis. The alternative can just be greater than that or less than that or even not equal to it. That's called a two-sided alternative. And it really depends on the context and the hunch of the researcher whether or not you're going to choose a one-sided or a two-sided alternative hypothesis. A significance level is let me put it this way. It's saying if the null hypothesis does happen to be true, how much am I willing to risk making the wrong decision of actually rejecting it? If rejecting the null hypothesis, if it's true, would be very dangerous, you might want to set your alpha to be very low, 0.01 or even smaller. 0.05 is the arbitrary typical value that's used. It could be at 0.10 if you want it to be higher, if making the mistake isn't such a big deal. But when you reject the null hypothesis and it happens to be true, that's called making a type 1 error. So we're going to be limiting our risk of making a type 1 error by setting alpha lower. The lower alpha is, the more strong we need the evidence to reject the null hypothesis. That's the idea. The test statistic, it really varies from hypothesis test to hypothesis test. Let me put it this way, sorry. The test statistic that we need depends on the type of test we're doing. So if we're testing the population mean, our test statistic will be a t statistic, which is calculated in this way. We are going to put it in use this formula, x bar minus mu naught over the standard error, the sample standard error. And this test statistic, t, under the null hypothesis will follow a t distribution with n-1 degrees of freedom. So what we have is some test statistic, a random variable essentially, that has its own probability distribution. Thus, we can calculate a test statistic from the data, see where in the distribution it falls. If it falls out in the tails, that means it's really extreme and unlikely under the null hypothesis. You get it? So the p-value is essentially the tail probability beyond the test statistic in its distribution. It calculates what's the probability of getting a test statistic as extreme or more extreme than we observed, if the null hypothesis were true. It's, in a sense, it's how plausible is the null hypothesis in light of the data. Okay? It's a little bit different than that, but that's a good way to think about it for your first pass through statistics. The p-value, it's a probability, so it's from 0 to 1, and it's and so the higher the p-value, the less inclined we are to reject the null hypothesis, because that means the null hypothesis is in line with our data. If the p-value is really, really small, that means that we would be more inclined to reject the null hypothesis. And if you need to have a threshold, you use alpha. So if your p-value is lower than alpha, you say my evidence is strong enough to reject the null hypothesis. Or you can kind of think of it like it would be extremely unlikely. If the null hypothesis were true, it would be extremely unlikely to get data like I have. Therefore, I will reject the null hypothesis. I don't think the null hypothesis is true. And that's the idea of the p-value. And it's important to remember it's not that the p-value is not the probability that the null hypothesis is true. That's not it. It's how plausible how likely is the data that we got under the null hypothesis, right? The point is the null hypothesis it's either true or false. There's no probability about it. It's either true or false, all right? So you can't say what's the probability the null hypothesis is true, because the null hypothesis isn't a random thing. It's either true or it's false. It's if the null hypothesis were true, how likely is data like we have? That's something that could happen with probability because it has to do with random sampling. So the idea that I was saying is, if you find your test statistic, put it into the distribution. If you're doing a two-tailed test, you would calculate the area in the tails, the symmetric tails, and that area is going to be your p-value. It's calculated using the t-distribution probability, right? We'll look at the code. For an upper-tailed test, you would calculate it in the upper tail. For the lower-tailed test, you calculate the lower tail probability. So it depends on the type of test you're doing. We'll see that in examples. Again, smaller the p-value, the more evidence, the stronger the evidence is against the null hypothesis. So our conclusion is either we reject the null hypothesis because we have significant results that are, or we could say that we have strong evidence against the null hypothesis, or we would say we don't reject the null hypothesis. We don't say we accept the null hypothesis because the null hypothesis was accepted before the test even began. We went into the test already assuming the null hypothesis to be true. We haven't proved the null hypothesis true. All we've done is failed to disprove it. All right? We're not in the business of proving null hypothesis true. That's not our job. Our job is to collect evidence in favor of the alternative. If that evidence is strong enough, we reject the null hypothesis in favor of that alternative. But we never prove the null hypothesis to be true. Okay? And the conclusion we reach, we should state a conclusion that is a clear conclusion in the language, in the context of the original problem. It should be a non-technical. This is really important, and this is absolutely true in my experience teaching statistics. Oftentimes students will just give the p-value and say, I reject the null hypothesis, and think they're done with it. That's no good. You have to think about, you have to imagine yourself doing this analysis and then presenting your results to your supervisor who does not know a thing about statistics. They want you to answer the question, is the on average, are adults overweight? You have to come back and say, the evidence from the data strongly supports the conclusion that on average, adults are overweight. Something like that. That would be a clear conclusion. Or if you'd say, there is not sufficient evidence from this sample to conclude that adults are overweight on average, right? You would make a statement, a concluding statement that is non-technical. You shouldn't be talking about p-values and alphas and t-statistics and stuff in your concluding statement. It should be clear language, non-technical, that any Joe Schmo would understand. Or Josephina, Schmosephina. So here's an example then, doing the test for body mass index. Now this is actually calculating the t-statistic and the p-value manually. So what we get here, we get the mean, the sample mean. So sampling from this data set, and then we're going to see if the sample mean is significantly larger than 21.7. And so the t-statistic, this is the formula that calculates the t-statistic, it's 11.38. And a rule of thumb, if your t-statistic is ever more than 3 or less than -3, it's extreme. Think of the empirical rule, the 68, 95, 99.7 rule. 3 standard deviations from the mean is 99.7%. So we have here 11.38. That's out in the stratosphere. That's really extreme. Okay, that's very, very, and the p-value shows it. The probability out in the tail is only 0.0000 20 zeros before you get to 1. So that's that's infinitesimally small, practically. It's really, really little. The chances that the population mean is 21.7, and yet our sample gave us, a sample mean so giant, it's virtually impossible for that to have happened. Now this is just showing the faster way to do it, which is what we'll be doing typically, is you use the t.test function in order to do the test. We actually just put in a couple little things, and then we run it. It gives you the results of the one sample test. It gives you the p-value to be, it says less than 2.2 e negative 17. That's less than, that's the smallest number it will give you for these, which is basically 0. Yeah, and it also is going to give you a 95% confidence interval. This is actually giving you a one-sided confidence interval, which is called a confidence bound. But what we're interested here is it gives you the t-statistic and the p-value, and you can interpret those. Two-sided. If you ever do a two-sided test, they're a little bit more conservative, which is to say that the p-value would always be twice as much as the one-sided test, because you're going to basically be doubling the p-value. You're making it less likely that you're going to reject the null hypothesis, and so you'd only use a two-sided test if you have no hunch about the parameter being greater than or less than some null value. If you just think it's different, but you have no kind of idea about whether it's more or less, you'd use a two-sided test. Okay, so I think that's all I'm going to cover. We'll be spending time doing lab, understanding the kind of the nuts and bolts of doing hypothesis tests and confidence intervals. This is going to be our foundation for the rest of the course, and really hypothesis testing is really the main thing that we'll be spending our time doing. Just looking at all the different types of tests you could try to do, testing all these different kinds of parameters and types of samples, two populations, and all of that. That's all to come. Looking at testing categorical variables versus numerical variables and so forth. So all this is to come, but this is a good foundational kind of lecture, I think, to get you some of the key ideas. All right, well, that's all I'm going to say. I'll see you in class.